So we want to consider the Earth as a series of spasmodic, catastrophic, terrible events, actually, that have taken place. And the reason we want to understand that is because those are the kind of events that life has responded to. The organisms that are alive at the time the events happen, some of them have the right characteristics. They are able to reproduce in a certain way. They can get food in a certain way. They're actually in an environment that was less affected than others. But they have characteristics that they've evolved that then would allow them to be more successful than others when the environment changes. So one of the most striking ones, and especially relevant to the modern day discussion in our society about global warming, is the idea that the Earth has been much warmer than it is now, and that it was especially warm during the time of the dinosaurs in the Cretaceous. But another time period that is equally dramatic, but in the opposite direction, is about 0.6 billion years ago at the end of the Proterozoic. The entire Earth froze. We had ice sheets that moved all the way from the poles down through the mid-latitudes and ended up with sea ice on the equator. And we call that Snowball Earth. Now there's discussions about Snowball Earth, about whether or not it happened and then to what degree it took place. Some scientists now are suggesting that maybe we had a slush ball Earth, where instead of having true ice at the equators, we had slushy ice at the equator. But the bottom line is that the Earth's temperature had dropped dramatically. And in that process, as the Earth cooled, then water was drawn out of the oceans and then formed ice sheets, both on the continents, but then it spread out onto the open oceans as well. So the Snowball Earth is dramatic, and I want us to visit just briefly what some of the evidence for this is. What are the things we can look for in the geological record that are a fingerprint of a glacier? And one of the most easy to find and least controversial of these are what we call dropstones. And a dropstone is simply the idea that a piece of rock that made up a continental landmass was gouged and ground and brought up into an ice sheet that formed on a continent, which we call a glacier. Then that ice moves and creeps slowly out towards the open coast and into the ocean. And when it gets to the ocean, it breaks into pieces and it forms icebergs. So when those icebergs that have the rock material that they derive from the eroding continent they were on, when those icebergs float from the northern latitudes into the equator, then they melt. And as they melt, this load they have of rocks, it drops out of the bottom of the iceberg and it falls down onto the seafloor. So that deposit we call a dropstone. And it'll have the rock types of the landmass on which the original glacier was formed. So those dropstones at the equator indicate that we had a very much colder Earth. Now we have other lines of evidence that has to do with the chemistry of some of the rock deposits at that time, and some of that chemistry, such as the oxygen isotopes, allow us to reconstruct what the temperature was directly of the seawater at that moment. But taken as a whole, the dropstones along with this other data is indicating that yes, we had a very cold planet, and yes, we had ice sheets at the equators, temperate ice sheets, and then ice covering the equator. So that's one thing, good dropstones at equatorial zones in the oceans. Now the next one is at the same time that all of us have some strong familiarity with metal, iron ore. Every one of us who go into a building in which there's iron girders, every one of us who have ever ridden in a car, every one of us who have ever taken a plane ride, we're all familiar with iron and different types of ores. So this is something that might not be unknown to you, but you might not have thought about where some of the metal comes from that, let's just say, it makes up your car. So it turns out that during this Proterozoic time period, and actually back into the Archean as well, in the deep oceans, we had fluctuations in the amount of oxygen, the amount of nutrients, and also the amount of dissolved metals, things like iron. Iron becomes dissolved when the oxygen drops to low levels within the ocean, whereas when the ocean becomes well oxygenated, then the iron chemically bonds with the oxygen and it precipitates a metal ore. So the thing that we want to think about there is that we have a fingerprint of microbial mats and microbial activity on the deep seafloor in a very unique kind of deposit called a BIF, a banded iron formation. And banded iron formations are ubiquitous around the planet in these age rocks. Now, if they're ocean rocks, and a lot of the rocks that are preserved at this time were deposited in the deep ocean. So banded iron formation is composed of the following. Imagine you're very deep down into the ocean, far below where sunlight is able to penetrate. So on the order of kilometers in water depth. And on that seafloor you have organisms that are forming these gooey, ooey microbial mats, and those organisms, they don't use oxygen, and they also are not able to photosynthesize. And so they have to have a lifestyle, and that lifestyle for them is they basically breathe iron. So iron 3 is taken into their cells, and then they use that iron to actually generate proteins and actually create energy, ATP, the basic currency of life. So they're going about their lifestyle just trying to survive and using the raw materials that they can get their hands on, which in this case is iron. So in that process of bringing iron into their cells and utilizing it, they can drive the precipitation of the iron into a solid mineral. And those solid minerals are forms of hematite and goethite and some of the other iron-rich metals that we see forming. So when you have microbial mats and these organisms are going about their lifestyle, they bring iron to the cell, and the end result is they precipitate the iron ores. So you get a pure iron ore that's driven by the metabolic activity of microbes that are living on the seafloor. And these pure iron ores come out in finely layered, stratified rock deposits called banded iron formations. Now they're different from stromatolites in that stromatolites are sedimentary rock deposits. These are also sedimentary, but they're not made out of sand grains. They're not made out of individual grains and clay components. They're actually composed out of metal minerals that are precipitating out of seawater and driven by the metabolic activity of the organisms. Now, banded iron formations are very beautiful. Oftentimes the iron oxidizes to a bright red, so if you see it in a rock outcrop, it has these beautiful layers and are on the order of tens of millimeters to maybe a single millimeter and even thinner in thickness, and you have layer upon layer upon layer. And so you see these bright red layers that are intermixed with oftentimes a gray to a black, and so those also have some metals in them, but it's also other types of sediments or mineral precipitation on the seafloor. In the end, it makes these beautiful banded iron formations, BIFs. And the BIFs are important because they're a good indicator of ocean circulation in the ancient oceans and also the activity of these ancient microbes. So we find BIFs primarily concentrated in the Archean time period, then up through the Proterozoic. So this is the type of fingerprint we see in the rock record that tells us definitively we had a deep ocean, lack of oxygen, iron was mobile and available to these organisms to breathe, take into their cells. The end product is to precipitate these iron ore mats. You drop a stone from a melting iceberg that's just above it, a few kilometers in water depth, and then you continue the process forward.